Hello, this video includes some additional practice problems for forces at angles. If you have not already watched the original video with forces at angles, I recommend you go back and watch that because there are some basic skills presented in that video which I won't be going over again as I approach these problems. So try and watch that one first if you can. So in this first problem here, it says that we've got an object underwater. Hopefully underwater should indicate to you that there's a buoyant force, but then I directly say it there. And then I said that there's a forward force coming from the current of the water, and I ask you to figure out what the magnitude and the direction of its acceleration are. And so in this problem, first thing I'm going to do is make an FBD. We've got gravity going down. We've got our buoyant force going up. There is no normal force here because there's not a surface pressing against another surface. And then, as I said, we have this applied force, I'll call it, coming from the current, which is going forward. Right, the gravitational force is a 4 kilogram object, so it's 40 newtons. Buoyant force I gave you was 70 newtons. And the applied force I gave you in the problem also, it's 30 newtons. And so that's all the forces that are happening on this object. Now for a second, I want you to take a moment to think about the direction of the unbalanced force in this problem, because that's crucial to knowing what the next step of this is. So think about that for just a second. Okay, hopefully you realize that the unbalanced force is going up and to the right. All right, so we create what I call an unbalanced force diagram, which we create whenever there's an unbalanced force that happens at an angle. And what it does is it basically breaks down the unbalanced force by putting it into components. All right, and if you look at the force diagram that we've done already, you can see how unbalanced it is in the different directions. If you look left and right, it's unbalanced by 30 newtons. If you look up and down, it's unbalanced by 30 newtons. All right, because it's 40 down and 70 up. All right, and so what we've got here is an unbalanced force that has components of 30 newtons to the right and 30 newtons up. We have to find a direction here, and I want to know what that quantity is, so we have to do some trigonometry. Doing the Pythagorean theorem, you can figure out that the unbalanced force is 42.4. 42.4 newtons going up and to the right. And then to figure out this exact angle here, this theta, what we can do is we know that theta equals, I would use the inverse tangent. Anytime you want an angle, you have to use an inverse trig function. Tangent makes the most sense here because we had the opposite and the adjacent sides. So opposite over adjacent, so 30 over 30. And if you put that into your calculator, you should get that it's a 45-degree angle. You might have also identified that it's an isosceles right triangle, which is a 45, 45, 90 triangle, and then you wouldn't have had to do the inverse tangent, but generally speaking, the step would be to take the inverse tangent, so I wanted to show you that. And so now that we've got this, we know that Fu equals 42.4 newtons at 45 degrees above the horizontal, which I'm going to say 45 degrees ATH, above the horizontal. All right, now it asks actually for the acceleration in this problem, and so we need to take advantage of the rearrangement of the Fu equals ma equation. We know A equals Fu over m, which equals 42.4 over 4, which equals 10.6. And that's meters per second per second. And the direction that it is at 45 degrees above the horizontal. All right, problem number 2, we have another one that is similar to that first one where we end up with an unbalanced force that is not on one of the axes, and so we're going to end up making an unbalanced force diagram again. But to start off with here, I'm just going to add the forces that it gives us. We know that there's a gravitational force on this, Fg, and it's a 10 kilogram model rocket, so that's 100 newtons. All right, the only other force we have here is this propulsion force. All right, which I'm going to call an applied force. And we know that that is equal to 300 newtons. Okay. And then what we need to do to try and analyze this situation, first of all, there's no other forces on this. A rocket doesn't have a normal force because it's not in contact with anything. I should have said assume there's no air resistance or friction or anything, but there are only two forces acting on this. There's the propulsion force and there's gravity. Now, to get a good idea of what's going on here, we've got to break this propulsion force down into two separate subforces. We know that this is 55 degrees here. And so what we can do then is do some trigonometry on this triangle, and we find out that the rightward the horizontal component is 172 newtons on the side there, and then 246 newtons going up for the vertical component of it. All right, so I just used trigonometry to break down that triangle. Now again, think about the direction that the unbalanced force is going in this problem, because it's not a nice, simple case. It's unbalanced both in the vertical direction and in the horizontal direction. Again, it's going to be going up and to the right, and we have to think how much is it unbalanced in each direction. So left and right, there's a force to the right that's 172. There's no force to the left, so left and right is unbalanced by 172. Up and down now, we have a downward force of 100 and we have an upward force of 246. So it's unbalanced by 146 newtons. I'm going to make this a little bit larger so that I can write my angle in there. Okay, so thinking about this, the next thing we're going to do is we've got to figure out what this theta is here, all right, and we've got to figure out what the hypotenuse is, because this is no longer at 55 degrees. The triangle that had side lengths of 172 and 246 had an angle of 55 degrees. This has a different angle. It's just as long, but it's shorter, so we have to figure out what our theta is. To figure out theta in this case, again, we're going to use the inverse tangent. Opposite over adjacent, so 146 over 172. You do that and you should figure out that it's 40.3. The other thing you're going to do is use the Pythagorean theorem, 172 squared and 146 squared, and then the square root of those added together, and you get 226 newtons for the length of that hypotenuse there for your FU. Okay, and it again has asked for the acceleration. So what we need to do is we need to take that FU and divide it by m, because we know acceleration equals FU over m, which equals 226 over 10, which equals 22.6 meters per second per second. And the direction that that's going in is it's at 40.3 degrees above the horizontal. So problem number 3. This one again is kind of similar. We're going to have an unbalanced force that's happening at an angle. We've got an acorn falling down from a tree. There are a couple forces on this acorn here. We've got gravity going down, half g. It's 1 gram, which is 0.001 kilograms, which means that the gravitational force is 0.01 newtons. The other force that we have on here is a wind force. Now, in this case, I asked what is the magnitude of the wind force, so we don't know what it is. All right, but I gave you acceleration in this problem, which is something that's going to be helping us. So if you look at the picture here, and I ask you what direction the unbalanced force is in, you should hopefully identify that the unbalanced force is going down and to the left. Sorry, so we're going to make an unbalanced force diagram again. It's going down and to the left. We don't know the side lengths of it just yet. We know actually the down part of it is 0.01. All right, but we don't know how much leftward we've got. But what we can do is we can use Fu equals ma to figure out how large this unbalanced force is. So the mass is 0.001 times the acceleration, 11.2. And you get 0.0112. So we know our unbalanced force is equal to 0.0112 newtons. Now we have a right triangle and we have two sides of it. So you can use the Pythagorean theorem and figure out that the other side is 0.00504 newtons, all right, using the Pythagorean theorem. And then to figure out I asked for the angle it makes with the tree. All right, first of all, I should say that this component, the horizontal component of that unbalanced force, has to equal whatever our applied force is there, because that's the only horizontal force. And the gravity was the vertical part of it, because that's the only vertical force. So we've got 0.00504 newtons for our applied force. All right, so that is one part of it. And then the other part is that we have to figure out what angle this is. And the angle that it falls relative to the trunk of the tree, that's a little bit confusing, but if you think about a trunk, right, a trunk is going up and down, and I'm asking you for the angle relative to the tree, all right? And so what I'm asking you for here is actually this angle here, this one here. All right, and so you should hopefully identify that in the picture, it's this angle here that I want. That's my theta. And so I'm going to calculate theta here. I think the one that makes the most sense to use is the inverse cosine in this case, because the sides that we knew were the adjacent side, that 0.01, and the normal force we calculated before we calculated that last side. And so I'm going to use the cosine inverse. You could use any of them as long as you're confident in the answer that you got for the other sides of the triangles, but cosine inverse makes the most sense to me. So cosine inverse of adjacent over hypotenuse, so 0.01 over 0.0112. All right, and if you do that work, you should figure out that the degree there is 26.8 degrees. All right. So that's the angle that we have, and we know that the F applied from the wind equals 0.00504 newtons as well. Okay, moving on to problem 4 here. We've got a truck, and it's driving up a hill, and then it says the driver sees a child and slams on the brakes. She has an initial velocity of 20 meters per second, and she travels a distance of 15 meters before coming to a stop. I say she doesn't hit the child, which is good. And then it says, what's the magnitude of the friction force? And so in this problem, hopefully you've identified that it's an inclined plane problem because we've got an object on a hill. All right, and so that means what we're going to do is we're going to put the forces down. All right. We're going to start off here and think about the forces acting on this. And again, actually, I like to err on the side of a really large force diagram for these ones. So I'm going to try and make it pretty big. We've got Fg, which is down here. All right, and then there is a normal force between the truck and the slope there, and the normal force should go perpendicular to the slope, so it's up this direction. All right, and then there's a friction force which is going down the slope, which should be at a 90-degree angle from that other force that you have on there. So I'm going to try and get this a little bit better. is slightly better. Okay, there's a friction force here, FFR. This is Fn. All right, and those are the forces that we have acting on this truck. And so what we want to do every time we have one of these inclined plane problems is I want to try and break down the gravitational force. In this case, because that friction force is on that left side there, I'm going to break it down by extending the normal force down this way. All right, and then it needs to make a right triangle here. So I break it down that way and try and get these two components here of the gravitational force. On every inclined plane problem that we do, it works out this way. All right, we have a normal force, we have a gravitational force, we usually have another force, although not always. We break the gravitational force down into components that are in line with the normal force and perpendicular there, and this is how it works out. The other important thing we've got to do here is we've got to figure out the angle that's involved, and so I make this little snowflake. Should look something like that. And then you have to try and find this angle in our little snowflake. Hopefully you can find that it's here, 15 degrees. All right, and then the complement of 15 degrees is 75 degrees, and then 15 degrees, and then 75. Going around, just going back and forth, 15 degrees, 75 degrees, 15 degrees, 75 degrees. All right, then we look in our picture where we've got the gravitational force, right? And you should see that on the top angle of the gravitational force, we've got something that looks like this and something that looks like this. All right, so something that's going down and something that's going off to the bottom right. And so hopefully that helps you identify that this angle in here is a 15-degree angle. Okay, so then what we can do, we know the gravitational force because it's a 1,000 kilogram truck. So it is 10,000 newtons. That looks stupid. 10,000 newtons. All right. And what you can do, that's the hypotenuse of this right triangle. You've got one of its sides is 15, so you can break it down into components. What you get is that this component that's in line with the normal force is 9,962 newtons. All right, and the component that's along with the ramp or along with the hill that's going down the hill is equal to 872 newtons. All right. And we know that this object is going to be accelerating down the hill. So something else that's known here is we know that it comes to a stop in 15 meters, all right, and that it had an initial velocity of 20 meters per second. So before we work any more on this force diagram, what I'm actually going to do is do the motion analysis on it. So we've got a velocity versus time graph here. And then on this, we know it starts out at 20 meters per second and it's coming to a stop. All right. We know it traveled a distance of 15 meters, so this side, this area here is 15 because it's traveled 15 meters. The initial velocity this side here is 20. All right, and basically we know 1/2 times 20 times however long that took, whatever the t is, equals 15. You solve that for t and you get t equals 1.5 seconds. Okay, and then we can find the acceleration. Acceleration equals change in velocity over change in time, which in this case equals 20 over 1.5. Which gives us 13.3 meters per second. Okay, that's our acceleration. From there, I know there's a lot of steps, but we can figure out what the FU is, because FU equals ma, which equals, in this case, 1,000 times 13.3 which equals 13,300 newtons. That's our FU. Now, this is where we go back to interpreting our force diagram. We know that the normal force, we know it's not accelerating in that direction of the normal force because it's not taking up off the hill. It's not taking off away from the hill. It's not like burrowing down to the hill. And so we know in the direction of this normal force, it has to be balanced, which means that this is 9,962 newtons here. The unbalanced part is the part that's going down the hill. Now, there are two things that are going down the hill, right? There's the gravitational force, which is going down, and there's a frictional force, which is going down. And so we know that the frictional force, FFR, and the gravitational force together have to give you your unbalanced force, which in this case is 13,300. And the way that we know that is the unbalanced force is going down the hill, and both the friction and the gravity are going down the hill, so together they add up to 13,300. And so we know then that the friction force is going to equal 13,300 minus the 872, which equals, in this case, 12,400 approximately. It's because we had some rounding earlier on, and so I'm going to keep it to that same level of precision to the hundreds place, so about 12,400 newtons for our FFR, for our friction force. So jumping to the back of the sheet, this problem is actually quite a bit easier. I give you the FBD, and it just asks you to calculate the magnitude of the unbalanced force in the direction. Something to think about here. We know that the unbalanced force is going to be going down and to the right. And so I'm going to break it up this way. And the reason that I'm going to have that horizontal force on top is because eventually I'm going to want to figure out what the angle is below the horizontal. And so that's why I didn't dot the forces the other way. I think it's good to have the theta be between the horizontal force and your FU, so that we can give the theta below the horizontal in this case. But that will come out as we go through the problem. And so things we know it's unbalanced by 40 newtons in the horizontal direction. We know it's unbalanced by 30 newtons in the vertical direction. This force is going this way and then down. And then what we can do is we can just use the Pythagorean theorem and figure out that the magnitude of the force is 50 newtons. All right, so a squared plus b squared equals c squared is all we did there. To figure out what theta is, we're going to do, in this case, the inverse tangent, I think, makes the most sense because we were given the 30 and the 40. So tangent inverse of opposite over adjacent, so 30 over 40. And what you get there is 36.9 degrees. All right, and so what we know is that FU, in this case, equals 50 newtons at 36.9 degrees below the horizontal. All right, which again is why it's important that I drew it the way that I did, because if you had done it the other way, you would have got the angle that was the complement to 36.9 degrees, and it would be off of the vertical, which is not as helpful. So I think drawing it this way is the best strategy. For problem number 6, we've got a sled being pulled. Things that I know that it's accelerating at 1.5 meters per second. Also, I can make the force diagram for it, even though I don't have all the pieces yet. I know that Fg for this sled equals 80 because it's an 8 kilogram sled. Other things I know, there's a normal force going to be on it because it's sitting on a surface. All right, and then we've got this tension force, which is going up this way. This is our Ft. All right. All right, and we're going to break that into components here. Now, something to think about with this problem is that it's going to end up being balanced in the vertical direction, up and down, because it's not taking off up into the air and it's not burrowing down into the ice. And so the vertical direction is going to be balanced. The horizontal direction is what's going to be unbalanced. It's going to be accelerating to the left. And so our unbalanced force is really just going to be that leftward component of the tension force. Vertically speaking, we should end up with a balanced force here. And so here's what I get. We know that Fu equals ma. All right. We know that it's an 8 kilogram sled and that its acceleration is 1.5 meters per second. All right, and if you multiply those by one another, you get 12 newtons for our unbalanced force. Now again, think about what direction the unbalanced force is pointing in this problem, because that helps you identify where that 12 goes. This sled is going to be accelerating to the left, which means that this leftward component of the tension force, that's the unbalanced force. That's 12 newtons. Then what you can do is you can use trigonometry to figure out the other sides of the tension force, because I'd asked you to find the magnitude of the tension force. That was the whole point of this problem. So 12 was just that horizontal component of it. You can figure out that the vertical component of it is 6.9 newtons, and that the tension overall is 13.9 newtons just by using trigonometry. All right. And then, it doesn't ask you this, I don't think, but you can figure out the normal force in this case as well. So you wouldn't have to do it, but it needs to be balanced up and down. Downward, there's an 80 newton force. Upward, we already have 6.9 newtons. So if you have, going upward, 73.1 newtons, all right, then you end up with 80 newtons going up. So we know that 73.1 newtons is the normal force. Ft in this, we calculated already, is equal to 13.9 newtons in the direction of 30 degrees above the horizontal. And in this case, hopefully it's pretty clear that it's going to the left. And then FU, I had asked you to find the direction there, so this is going left as well. All right. So F tension is up and to the left, and then we've got the unbalanced force there. Okay, problem number 7. We've got another inclined plane problem here. In this one, it's a child going down a slide. There's no friction. All right. So all that we've got on this problem here is a gravity going downward, Fg, and the normal force from the slide. Fn, and nothing else. Okay, that's it. So what we're going to do is we're going to break down the gravitational force into components, just like any other problem. We have to figure out here what angles we've got, so I do that thing where I make that snowflake again. We know here that if you identify this angle in the snowflake, it is 40 degrees here. And then you could just go around 40, 50, 40, 50, 40, 50, 40, 50. All right, then you want to identify the angle at the top of the gravitational force, and you should hopefully see that this is 40 degrees as well. Something else we know is that this is a 30 kilogram child, so it's 300 newtons for the gravitational force. You can use trigonometry then to figure out the other sides of this. We get 193 for the side that's going down the slope, and we get 230 for that one that's perpendicular to the slide. Now, what we get here then, this is going to be accelerating in the direction down the hill. So in the direction that's perpendicular or normal to the hill, it's not going to be accelerating, which means that 230 that we have going in the direction perpendicular to the hill is going to cancel out with this normal force. And that's going to be 230 newtons there. The unbalanced force in this case then is that 193. All right, and then we know Fu equals ma. All right, or A equals Fu over m. And we can calculate from that A equals 193 over 30, 6.43 meters per second, and the direction of that is down the hill, or down the slide in this case. All right, on to this last problem. This one's not so hard as long as you work out the different forces that are coming into play here. There's kind of some atypical directions for some forces here, but as long as you think it through, I think this one is actually pretty easy. So the things that we know here. We've got a block, it's sliding up a wall. There's a friction force resisting it, all right? And we know that the block has a mass of 1.2 kilograms. And so there's going to be a gravitational force on it, Fg. That's equal to 12 newtons. Additionally, in the downward direction, because it's sliding up the wall, the friction force is going to be pointing downward, resisting the motion. So we're going to have a friction force, which equals 3 newtons. Also pointing off here to the left, we're going to have a normal force. And then pointing to the right and up, we have this force, this normal force that's coming in from the person who's pushing it up the wall. And some things that we have here, if I break this down into components, I know that this is a 30-degree angle here. Additionally, we know this normal force, Fn here, has a magnitude of 20 newtons. So what you can do then is you can use some trigonometry and break down the sides of this triangle, and you should get that the horizontal component of this triangle is 10 newtons. The vertical component is 17.3 newtons. All right, and then in this one, it's kind of different than the other things because if you think about the direction it's accelerating, or the direction that the unbalanced force is facing, it's going to be accelerating in the upward direction, which means it's unbalanced up and down. It is not accelerating in the horizontal direction, which means the left and right forces need to be balanced in this case. If you think about that then, the left and right forces needing to be balanced, this normal force has to equal 10 newtons to counterbalance that force on the other side of 10 newtons going to the right. To get the unbalanced force, we have to think of the up and down direction. So what we've got here is we've got a 12 Newton force down from gravity and another 3 Newton force down from the friction, so that's a total of 15 newtons down. And we've got a 17.3 Newton component, upward component of that normal force going up. All right, so that's 17.3 newtons up and 15 newtons down, which comes to an Fu of 2.3 newtons in the upward direction. Next, we need to calculate the acceleration, which is equal to Fu over m, which equals 2.3 over 1.2. And if you calculate that, you should get 1.93 meters per second. And the direction here is up, or upward. Looking over these problems, hopefully you've seen a bunch of different patterns that come up in the way that they're approached, a bunch of different common strategies that we use. Try and make sure that you have a full understanding of all of these problems, and if there are any questions, make sure that you come in and ask.